It's a great pleasure to have Professor Kaladi Babu from Oklahoma State University tell us about unified framework for flavor anomalies, Muon, g-2, and neutrino masses. So please.
Thank you very much. Yeah, I think it's a great pleasure to give this presentation based on my recent work. Of course, it would have been even better if it were in person, but under these conditions, this is the best we can do. And hopefully things will change quickly everywhere, and we will be free to travel as of 2 years ago. I was just mentioning to Muon that my last international travel was to Kiev about 2.5 years ago. I had a great time. There was a workshop in November, which I attended. I actually also visited Kiev more than 20 years ago. There was a to give some talks at the summer workshop that used to be held at Kiev. So both times I had wonderful time. Really enjoyed my visits. So today, even though it is remote, I'm very excited to talk to you about flavor physics, actually phenomenological flavor physics. And the main topics are the flavor anomalies, mostly related to Bdk, the g-2 anomaly of Muon, and neutrino masses. And the focus of this talk would be to kind of connect these various BSM possibilities together. So here is a rough outline of the talk. I will, although I'm sure that you have heard about all these anomalies separately or even jointly, I'll have a quick review of these anomalies. The Bdk anomaly, there are two types, neutral current decays of B, which is characterized by these two quantities, Rk and Rk star. There is an anomaly in the charge current decay of the B meson, quantified by Rd and Rd star. Then I'll briefly review the Muon g-2 anomaly. Then again, a short discussion of neutrino masses and oscillations in the context where one could also explain these anomalies. So the basic idea that I will describe is the idea of TeV scale leptoquarks. If you want to explain these anomalies listed here, it turns out that in terms of leptoquarks, one would need 2 leptoquarks if they are scalars. So I will describe the model based on this R2 and S3 leptoquarks. And it turns out that having 2 scalars with different couplings, Yukawa couplings, is also a required ingredient for generating neutrino masses through radiative corrections. So that is how I will be unifying the flavor anomalies with the neutrino masses and oscillation. And one of these leptoquarks can also generate the Muon g-2. Nothing is easy. We are doing flavor physics and at low scale of order TeV. There are a large number of constraints. I will go through various constraints, and I will eventually show that there are solutions to explaining these anomalies in terms of these leptoquarks. I will briefly also discuss the collider constraints and tests of these ideas. And towards the last part of the talk, I will describe possible connection between Muon g-2 and neutrino magnetic moment. The reason to discuss neutrino magnetic moment these days primarily has to do with the xenon 1-ton electron recoil excess that was announced about a year ago. One possible explanation of that anomaly is in terms of neutrino magnetic moment. Solar neutrinos, if they possess magnetic moment, they could they arrive at the detector, and they can lead to this excess recoil events with electrons at the xenon 1-ton. I will not describe in great detail these. We actually have 2 papers on that, but I will just focus on the connection between Muon g-2 and the neutrino magnetic moment. It turns out that once we explain the magnetic moment of the neutrino in a natural way, there is no room to fudge anything with the muon g-2. It's very interesting that the sign of the correction to the muon g-2 comes out in the right direction, and also the magnitude is of the right right type. So this is an explicit example that can be completely tested at future collider at the high luminosity LHC, for example. I'll describe that a little bit towards the end of the talk. But for most part, I will be discussing the flavor anomalies, muon g-2, and neutrino masses in terms of this R2 and S3 leptoquarks. Okay, so brief review of. By the way, I will welcome questions during the talk. So please feel free to interrupt me during the talk. You don't have to wait till the end of the seminar. Okay, so that was only the outline. So let me get to a very lightning review of these anomalies that I will try to address in this talk. It turns out that lepton universality appears to be broken in decays in the Bdk to k L plus L minus. This anomaly, this occurs in the standard model, and a typical contribution in the standard model for B to K L plus L minus is shown here. It's a penguin with a penguin diagram which takes a B quark to a strange quark through a top quark loop. And then from the W boson, there could be a gamma or a Z attached to them, right? In the standard model, the expectation is that when B decays to K E plus E minus, or B decays to K mu plus mu minus, the decay partial lifetime should be about exactly the same. The muon mass does give a small correction compared to the decay to electron, but since the muon mass is much smaller compared to the B meson mass, this kinematic suppression is very small. So if one constructs this ratio, B decay to K mu mu divided by the partial width of B to K mu mu divided by partial width for B to K EE, in the standard model, it would be very close to 1. Similarly, one can construct this decay rate, partial width of B to K star mu mu versus K star EE. In the experimental observation, primarily coming from the LHC-B experiment, the most accurate measurement at least, for when the invariant mass of the lepton pair is constrained to be in this range, 1 GeV to 6 GeV squared, the RK is measured to be 0.846 with the error coded there. And as I mentioned, the standard model expectation for RK is very close to 1. So this has been around from earlier experiments, Bell, Babar, as well as LHC-B. As far as RK is concerned, recent analysis with more data from the LHC-B collaboration decreased the error bar compared to a year ago by about 30%. The central value remains the same. So it used to be like a 2.5 sigma deviation from the standard model with the Muon 2021. This deviation is now discrepancy is at the level of 3.1 sigma. Okay, so this is one of the, and if you think about it a little bit, beyond the standard model appearing in the flavor sector, especially among muon versus electron, it's somewhat surprising. So many theorists probably thought that this anomaly would go away with more data. That hasn't happened so far. It doesn't mean that it won't happen, but this is a strong hint that we cannot. We may have to take it seriously. Okay, so that is about RK. RK star has a similar, the fundamental physics that affects RK will also tend to affect RK star. And it has a similar, what is shown here is RK star, the central prediction of the standard model is about 1. Now the LHC-B collaboration has provided RK star measurement in 2 energy bins. Again, Q squared is the invariant mass of the lepton pair. So they have a low Q squared bin as well as a medium Q squared. This is about 1.1 GeV squared to 6 GeV squared is a higher Q squared bin, and there is one below that. There is an anomaly even in the low Q squared bin, which is a little bit more statistically significant. But I think I should note that it is very difficult to explain the details of this low Q squared anomaly. And to my understanding, there are no consistent unified picture that explains both the high Q squared and the low Q squared anomaly. Well, there are attempts. There is a way of introducing a new particle for every bin, then one can do it. But that looks somewhat ad hoc. So for what in my discussion today, I'm going to kind of explain this low Q squared excess relative to the higher Q squared in RK star as a statistical fluctuation. In other words, I will not be explaining the lower Q squared bin. It is averaged over the low Q squared as well as the high Q squared. Okay. All right. So that was one type of anomaly in the Bdk, and the second type comes from the charge current Bdk anomaly. The charge current Bdk have to do with the Bdk into a d meson, tau, and a neutrino, and this occurs in the standard model through this kind of at a tree level through W boson exchange. One can connect B quark to charm quark through a coupling proportional to VCB, and the W boson can decay to L nu. In the standard model, this L nu could be electron, its neutrino, muon, and its neutrino, and tau and its neutrino. So one can form ratios, and the ratio is parameterized as RD or RD star, where B decays to D tau versus DL. L here stands for electron or muon. And in this measurement, the electrons and muons are averaged, so there is no distinction. It is found that these decays in the standard model expectation for these ratios is not 1 because the D plus tau mass is close to B mass, so the kinematics plays an important role. The standard model prediction for RD is given here, 2.299, and the RD star is 0.258. And the experimental value is a little bit higher compared to the standard model expectation. This is a plot from the heavy flavor averaging group, which has suggested the average of all these RD, RD star, and so on is shown here in the red oval region, whereas the experimental value is somewhere here. Sorry, the other way around. The average of the standard model prediction is shown here, and it is approximately 3 sigma away from the standard model, from the experimental value. So this is the second anomaly. And just to show one more aspect, for the RK B to S mu mu, this occurs through a loop. So any new contribution should be compared against the loop contribution. And because of that, it turns out that if we explain it in terms of new physics, the scale of new physics could be multi-TeV, for example, 10 TeV, 20 TeV, in order to explain the RK anomaly. On the other hand, the RD anomaly, since it occurs through at the tree level in the standard model, and discrepancies at the level of, say, I don't know, some 10%, it turns out that the new physics that explains the RD anomaly cannot be more than about 2 TeV or so. If it is perturbative, it has to be below about 2 TeV. And I will show explicit examples where we try to explain that in terms of leptoquarks. Okay, so that is anomaly number 2. And third one is which has got a lot of attention because of the recent announcement from the Fermilab experiment from the Muon G-2 collaboration. The anomalous magnetic moment of leptons can be measured as the Hamiltonian that interacts the magnetic moment with the magnetic field is given here. It is proposed the magnetic moment is proportional to what is called a G factor. This G factor for a Dirac fermion is equal to 2 as predicted by Dirac, but it doesn't stay as 2, and the deviation from 2 is parameterized as the anomalous magnetic moment G minus 2 divided by 2. This is computed very precisely in quantum field theory. In QED, the initial computation came from Schwinger. The actual answer to this AMU is alpha over 2 pi. This is a very important computation, and this actually justified the validity of quantum electrodynamics during the time Schwinger did this calculation. But since then, we have improved the accuracy of this evaluation very, very significantly. The QED component has been evaluated to some 3-loop order. There are electroweak contribution that have also been evaluated. There is also mixed hadronic contribution, which is shown here. This is the vacuum polarization contribution because so photon goes through a hadron loop back to photon, and it is important at the level of current accuracy of experimental accuracy. Now, it turns out that the Brookhaven experiment since 2006 had a discrepancy with the standard model expectation at the 3.7 sigma level. But recent Fermilab data, when combined with the Brookhaven data, is given that there is a discrepancy which is at the level of 4.2 sigma. So this is the slide from the Fermilab experimental paper. Here is the Brookhaven measurement. Here is the Fermilab measurement. This is the experimental average. And this is the standard model expectation. And that's for the 4.2 sigma. It should be noted that especially the vacuum polarization contribution to Muon G-2 may have some uncertainty. This is our best theory estimate based on QCD sum rule and as well as the lattice gauge theory calculation. Unless there is some big jump from the lattice calculation to go from this. This is the international collaboration of lattice people who have recommended this as the central value and the error bar. Unless there is some big discrepancy in that computation, this is a very significant discrepancy. I should also point out that there is at least one lattice collaboration which has claimed a smaller error, and that value comes closer to the experimental value. So this remains to be fully settled. The BMW collaboration has a value which is closer to the experimental value by within about 2 sigma. But that is this is something that we will know more about on the experimental side, certainly because Fermilab experiment is running and it is going to have more data. And on the theory side, there are more dedicated lattice research. So hopefully we will have a better understanding on where the discrepancy is coming from. But certainly on the experiment versus experiment, the Fermilab measurement is in good agreement with the Brookhaven experiment. This is really good. It is not just a statistical fluke as far as the experimental numbers. Okay, now the fourth thing that I would like to discuss in the same context is neutrino masses and oscillations. And I will be very brief about it. Everyone knows neutrinos must have mass in order for them to oscillate, and the oscillation parameters have been well measured. This is from a global fit. There is the mixing angles, the solar angle, the atmospheric angle, the reactor. Where is that? Reactor angle, and mass splittings have been measured. This can only be explained if neutrinos have mass, and as everyone knows, neutrino mass requires physics beyond the standard model. Okay, so here let me kind of digress. I will start from the understanding the neutrino mass from theory, and then connect it to the experimental anomaly. So the standard paradigm for understanding small neutrino mass is in terms of the Seesaw mechanism. So one generates Weinberg's dimension 5 operator, which here I wrote it as LL5 and phi is the standard Higgs doublet. And this is suppressed by some heavy mass scale. So one understands why the neutrino mass is small, because the scale at which the lepton number breaking effective dimension 5 operators is induced is very high. Okay, there are different realization, type 1, type 2, type 3. This is a fermionic seesaw. This is a scalar integrated seesaw. One feature of this is very elegant, okay, especially the one on the left side, very elegant. It fits into unified theories, etc. However, the scale of new physics in this mechanism could be very high. It could be as high as the grand unified scale, 10 to the 14 GeV. So any new physics at that scale would have very little impact on the B anomalies. So although this may be correct, this may have nothing to do with the B anomalies. And same with the Muon G-2 anomaly. So if the standard Seesaw picture is responsible for neutrino mass generation, that will not be unified in any easy way with the Muon G-2 nor the Bdk anomalies. Okay, so that brings me up to an alternative way of understanding the small neutrino mass. It has to do with, it is connected to radiative mechanism. So the basic idea is the following. It was suggested long ago, right after the Seesaw mechanism was proposed. The idea is the following. The neutrino mass is 0 at tree level. This may be because there is no right-handed neutrino. Okay. In that case, if lepton number is violated somewhere in the theory, then small and finite masses can be generated as quantum corrections. Now, typically, if you want to implement this idea, it involves the exchange of two scalars. And the reason I want to emphasize this here because the two scalars but two scalars is what is needed to explain the two anomalies in the Bdk. Okay. The reason why one would need two scalars typically is because you need to break lepton number. If there is a single scalar introduced to the standard model, you can also always assign a lepton number to that. And it is very difficult with a single scalar sector extended by one field. It is very difficult to write down a lepton number violating operator. So this is why it is very motivated to introduce two scalars to the theory. And the simplest example of this radiative mechanism is called the Z model. And sure enough, there are two scalars. The two scalars that are introduced is a charge scalar eta plus, it is a singlet, and a second Higgs doublet. Now, so as I mentioned, if suppose I only introduce the charge scalar eta plus, it couples two leptons to each other. L eta is allowed. However, that doesn't break lepton number because I can assign a lepton number of 2 units. If I have a coupling L eta, I can assign lepton number of 2 units to eta. That is the reason why, in addition to that, one must have something else. And that something else is provided by the second Higgs doublet. And of course, the second Higgs doublet, it couples to leptons as like the first Higgs doublet. So that also doesn't break lepton number. However, in the presence of two doublet and the scalars, you can write a cubic coupling. This is H1, H2, eta. H1 is a doublet, H2 is a doublet, H1, H2, eta is allowed. Then you see that lepton number is explicitly broken. Okay. So this is the rationale for the need for introducing more than one scalar in order to generate neutrino masses radiatively. So in this scheme, what happens is that the neutrino mass, the smallness of the neutrino mass is explained because there is a loop suppression. But also please notice that there is a chiral suppression. This chiral suppression, by that I mean that the neutrino mass is proportional to the charged lepton mass. Okay. And if that happens, for example, it could be electron mass or muon mass that goes inside times a loop suppression, then the scale of new physics naturally could be rather low at the TV scale. So I can go from, say, near grand unification scale to near TV scale. Of course, it doesn't really require it to be TV scale because, say, a loop factor, which is typically 10 to the minus 3 or so, times the electron mass, is still a little bit more than what you need for the neutrino mass. But that's okay, I think, because you don't need all the couplings that go into the neutrino mass to be of order 1. For example, the cubic coupling, which it doesn't have to be of order the mass of these particles, could be a little bit less. Okay, so it is not unnatural to have these scalars that induce neutrino mass at the TV scale. Okay, is there? This is the main idea, and I'm going to. I can actually tell you what the highlight of the model that I will describe. This is the general idea. This extends to arbitrary type of particles that you can think of. if suppose we decide that there are no extra fermions in the theory, then you must have two scalars. And here in the Z model, simplest choice was a doublet Higgs and a singlet Higgs. They are color neutral. But I could do exactly the same thing with the colored guy, right? If I use the colored guy, then interior fermion will be a quark. And then I'm inducing the neutrino mass through a leptoquark. In fact, these leptoquark models of generating neutrino mass this way have existed for some time, well before B anomalies were around. So in fact, I can even go one step further. The one step further from looking at the diagram is that remember that this way of producing the neutrino mass eventually is giving our Weinberg operator LL phi phi. One of the phi is associated with a charged lepton mass, and the other phi is here. Okay, LL phi phi. So with that structure, what is needed to connect this is that you need a doublet scalar and a singlet scalar under SU2. It could be colored, or the other option is a doublet scalar and a triplet scalar. You can replace by a singlet by a triplet, that is fine. And if I assume them to be colored objects, that would be the leptoquark model I will describe. It turns out that if I have a doublet and a singlet of SU2, that is not going to fit all the anomalies. However, if it's a doublet and a triplet, then it can explain all the anomalies. The doublet will be called R2 leptoquark. The triplet will be called S3 leptoquark. Okay, I will describe it in case. Yeah, I don't want to assume that you know all the standard notation for the leptoquarks. Okay, so that is this is the main idea. Let me stop and ask if there is any question on the general idea. Okay, if not, I will continue and I will ask for any clarification that may be needed as we go along. Okay, now I want to make one distinction between this kind of, going back again, this kind of neutrino mass generation model and another type, which I will describe in the next slide. And let me point out another aspect of this kind of diagram. I can cut this diagram in such a way that, let's say I cut it here on the left side, then the effective operator would be a dimension 7 operator involving only standard model fields. And that operator we can easily read off here. I have L coming in, another L coming in. So there will be LL, then this is EC is going in. So it will be LLEC and another LH. So the effective dimension 7 operator, but if I cut the diagram on one of the internal lines, it will be dimension 7 lepton number violating LLEC LH operator. Those who are familiar with the supersymmetry will immediately know that it's a product of two R parity breaking operators, LH and LLEC. That breaks lepton number by 2 units. Okay, so the main idea is that this once you cut the diagram, you get D equal to 7. You can actually go to a higher dimension and also generate neutrino mass. The lowest is dimension 7, but there are well-known models of dimension 9. Once you cut the operator, you get dimension 9 delta L equal to 2 operators. In principle, it could go to dimension 11. It turns out that in the standard model effective theory, lepton number is violated at these odd number dimensions. That's the reason why this is like that. So I already mentioned that if a loop diagram has at least one standard model particle, this can be cut to generate such effective operators. Now, it is important that in order to cut it, to write in terms of an effective standard model operator, there must be some line inside the loop that is a standard model particle. Now, this is unlike the model of, say, there is a well-known model called the Scalar model for neutrino mass generation. Where this is primarily due to Ganeshma. In this model, there is a second Higgs doublet. It is like an inert doublet, which does not acquire a vacuum expectation value. And there is some right-handed neutrino But since the inert doublet does not acquire vacuum expectation value, there is no Dirac mass induced. Nu connects with N, but there is no, it is only through this era which does not acquire vacuum expectation value. So all the internal particles have a discrete symmetry, which are odd under this Z2 discrete symmetry, and this provides a dark matter candidate. So this is very interesting that there is a connection between neutrino mass generation and dark matter. It could be either this lightest of this eta or the N. Now, this is a different way of neutrino mass generation. But as you can see, none of the particles inside the loop are standard model particles. And if I cut it somewhere, I will not get an effective operator in terms of standard model fields. So, and also this purely from the perspective of neutrino mass generation, there is no chiral suppression. The suppression is proportional to the some non-standard model particle mass. So it could be very, very high, right? So this diagram from the pure perspective of neutrino mass generation, the mass of the heavy guys could be at 10 to the 12 G. However, if you put in additional constraints such as need for dark matter, that would force these internal particles to be at the TeV scale. Now, so this is a different mechanism for generate. Well, it's related, but in principle, it's a different mechanism because it cannot be cut to generate this higher dimensional operator. And also, I should say that I will not be discussing this kind of neutrino mass generation, because as you can see, if there are no standard model particles, these interactions will not lead directly into Bdk anomalies or Muon G-2. So these are good for dark matter physics, and maybe for some flavor physics, but not for the B anomalies or Muon G-2, not directly. Okay. So now I described all the anomalies, and I want to discuss. I think I should speed up a little bit. But when I come to the actual model, I think I will go a little bit faster. So I think I already said that a pair of leptoquarks R2 and S3 can generate neutrino masses. R2 will explain RD star, S3 will explain RK. The same R2 can also explain Muon G-2. The flavor structure that is needed to achieve all these is very constrained. And this framework can be tested at the LHC, as well as in processes such as tau to mu gamma. This is the summary of what I will be doing next. Now, before I get to the model, I want to also say that leptoquarks, there are hundreds of, I apologize for not giving all the references to the leptoquark models. There are literally hundreds of them. Many of them propose to explain the Bdk anomalies. So I want to kind of update you in case it is necessary that there are strong limits. LHC has provided rather strong limits on masses and couplings of leptoquarks. So we did, when we looked at it in the context of our model, we did pretty much a model independent analysis. So before getting to the model, I wanted to kind of talk about that. Leptoquarks can be produced through gluon fusion, for example, in pairs. The leptoquarks can also be constrained by processes like this. PP goes to L plus L minus. The mediator will be T-channel leptoquark. And it turns out that recently, last year, within the last year, LHC has provided data which constrains these leptoquark masses and couplings, especially those connected to the first generation quarks, rather severely. Because of these constraints, some of the earlier proposals for leptoquark explaining the B anomalies seem to be not viable. This is a nice table from Angelescu and company recent paper. What they have, so there are various scalar leptoquarks and vector leptoquarks that can have, that can be well defined. By that I mean that couples a quark with a lepton. So among, you see that among the scalar leptoquarks, there is S3, S1, and R2. If you try to explain both RK and RD, you see that, certain, see, S3 can explain RK, but not RD. Therefore, not both. S1 can explain RD, not RK. R2 can explain RD, but not RK. So among all these scalar leptoquarks, it's difficult to have a single field explaining both anomalies. And actually, I'm not too unhappy about it, because if I want to explain the neutrino math, I need two scalars. So I can take two of these. Now, I should also point out that actually, perhaps a more elegant way would be, say, this U1 vector leptoquark. It can explain both anomalies, but introducing vector leptoquarks, it's not easy to UV complete, because it will be part of a gauge multiplet. You cannot add gauge bosons arbitrarily. So this one does actually fit into the Pati-Salam extension of the standard model based on SU4 color. And people have studied it. And I think you've had a seminar recently on explaining it based on this U1 leptoquark. It is, I think, more profound, but the standard Pati-Salam leptoquark gauge boson cannot do it, because there are other processes that it would mediate. K long to mu e actually puts the mass of this vector leptoquark gauge boson to be more than 1,000 TeV. So one has to fiddle with that constraint, and the simple idea of unifying quarks and leptons will have to be given up. I will not discuss much. I think it is, I mean, if one can do these with the vector gauge boson, that is my opinion, that is more profound, but it has its own challenges. Okay, and there is very little successful effort along this line compared to the scalar leptoquark. I'm not saying that there are no effort. There have been valiant attempts to explain these anomalies, but if you actually look at it, you will see that it is a real challenge. So I'm taking the somewhat more easy way, which I look at it like a bottom-up approach. Okay. So what about the mass of the leptoquarks? So this is from this paper of us last year. We looked at the, well, this is reinterpreting the LHC data, assuming for any given branching ratio, one can see that. You see that typically leptoquark decaying to electrons or muons, bounds are like 1.7 TeV. However, if it decays primarily or 100% of the time to tau and a light jet, the searches are not so strong, presumably due to challenges in identifying the tau and also light jets. You can actually get a leptoquark mass of order 530 GeV. But in fitting the data, one has to be consistent with all these constraints. So these are various decay modes as a function. And if you choose some value of the branching ratio to be, say, to lower the mass, we say if I want to choose as a nu j to be the dominant decay mode, then I should actually find the other decay mode so that the total branching ratio turns out to be 1. So that's not an easy task. And many of the early attempts had leptoquark masses of order 1 TeV. Yeah, there are some strong constraints on the branching ratio, which is 1 TeV. Okay, so this is our analysis of our interpretation of the LHC data from the T-channel leptoquark non-resonant production of L plus L minus pairs. These Fs are basically the coupling. 1, 2 stand for the U quark coupling to muon. The first index is going to be the quark index, and the second index would be the leptonic index. And you see that this is actually rather stringent. For 1 TeV leptoquark, none of the couplings can be more than 0.4. Even at 2 TeV, in explaining the anomaly, one could go to larger mass values, but then one would need larger coupling. But you see, again, this PP to L plus L minus gives a rather stringent constraint. So this is actually the reason why these are the constraints that a single leptoquark explanation is excluded by LHC data and other flavor constraints, of course. Okay, so now I will come to the model. R2 is a leptoquark with this quantum number. The electric charges are shown here, omega 5/3, omega 2/3, and the S3 leptoquark is this quantum number. And we call it the component to be omega for the R2 and rho for the S3. Now, I have to make one comment, which is that the R2 should mix with S3. And because of the hypercharges that they have, there is no direct mixing that is possible. And this is needed for neutrino mass generation. So we have to put a connector field. And that connector field, the simplest possibility is having what is called a Higgs quadruplet. This will connect these two fields. And actually a model for neutrino mass involving these fields was suggested by the Kiosk group a few years ago, not in the context of Popov and company, and not in the context of B anomalies. So they had the skeleton model written down. We found out that this is the model that can actually explain the anomalies and also the neutrino mass. So given these leptoquarks, these are the additional Yukawa couplings. So since I'm going to say a little bit more about these Yukawa couplings, so there are basically, there are 3 Yukawa matrices, which are called F, F prime, and Y. Now, so F couples to R2 leptoquark, F prime is also a coupling to R2 leptoquark, and S3 is, S3 leptoquark it is called Y. Now, the way RD will be explained is pure through the exchange of R2. Okay, and that is so that will be proportional to F times F prime. RK will be explained by pure exchange of S3, so that will be Y times Y. Okay, and F times F prime will also generate through a top quark internal loop the muon G minus 2. And the neutrino mass will involve F times Y. So although it might look like there are many parameters, once we include all these requirements, including all the oscillation parameters for neutrinos, parameters are rather constrained. Okay. So here is the neutrino mass generation. This is almost like the Z model. You have a, this is the triplet of SU2. This is a doublet of SU2. They mix through the quadruplet. And this quadruplet has, you can think of it as, it's similar to the type 2 seesaw, except that, well, it's a quadruplet. So it's, it goes into 3 Higgs doublets. So it acquires an induced vacuum expectation value. This vacuum expectation value could be quite small compared to the electroweak breaking scale. It has to be small from the electroweak rho parameter, but it doesn't give directly a neutrino mass, unlike the type 2 seesaw. It has to go through this loop. Okay, and the effective operator from this diagram, this is psi supposed to be L. This is psi H dagger H. But then, so this actually is dimension 7 operator. Then you might wonder why not connect one H dagger with an H and get a lower dimension operator. It does actually exist. You can connect these Higgs lines to get this one. But the flavor structure is exactly the same. So it doesn't matter. There's a 1 loop and 2 loop. They may be comparable because of the different dimensionality. So we keep both of them in place. It doesn't change any of our detailed discussion. It only changes the overall mass scale because the flavor structure is the same. So the flavor structure is of the neutrino mass is given by this F. The internal quark masses are the up quark mass. So this is the up quark mass matrix. And the down Yukawa coupling comes in. So we go to a basis where all the couplings are defined in a basis where the down Yukawa couplings, down quark masses are diagonal. So that's how the CKM matrix comes in between. Okay. This is a convenient choice. So this is we have to now fit this to all the neutrino observables. There's an overall scale and F times everything here, F times Y is fixed basically. Okay. That's how neutrino fitting will work. And the neutrino and the Yukawa, so there are three matrices, and these are the textures that seem to work everywhere. The zeros are not meant to be exact zero, they are just small numbers. If they are not zero, the constraints on them are rather severe from flavor violation. So we just took them to be zero. Okay, so now I think I've tried to make it somewhat easier to by color coding here. What happens is the G-2 will, okay, the first index here is refers to the quark, second index is to the lepton. The G-2 actually occurs through, so the Muon G-2, the second index here is F32, also second index, it can go through a top quark. So this is a chirally enhanced Muon G-2 contribution. So the coupling doesn't need to be very large because instead of the muon mass inside the loop, it's going to be the top quark mass. So the product will provide Muon G-2. Then RD and RD star comes from F again, also from F times F prime. Dominant contribution will be F prime 33, F23, F prime 33, F23. But you can also get a subdominant contribution from F prime 33, F22. So that is how, because in the decay, the neutrino in the decay for relevant for RD, neutrinos could be tau neutrino or muon neutrino. That's why the muon neutrino could also be relevant. In principle, even this 2-1 element could have been relevant, but because of mu2e gamma constraint, that has to be extremely tiny, so we set it to 0. Now, if you do this, then this reason for this putting this F33 is that we need a little bit of tuning, like at the 10% level. Otherwise, you will get too much of tau to mu gamma. So with a small F33, we can bring it under control. Then RK is explained by the pure exchange of the S3 leptoquark that goes like the product of Y22 times Y32. And then the other remaining of the Y23 and Y31 are needed to fit all the oscillation data for neutrino. So that's the framework. Now we actually go ahead and do it. So now I can go a little bit faster. The charge current anomaly, the new contribution to Bdk to Cl nu is given through this R2 leptoquark omega 2/3. It has this coupling, it has this coupling. And effective interaction Lagrangian is given by this. If I integrate out this omega 2/3, this is what you get. There is a scalar coupling, there is a tensor coupling. The tensor coupling and scalar couplings are going to be related because they come from the same diagram. What is needed is that the experimental value of RD and RD star are a little bit bigger than the standard model value. So we need some kind of a constructive interference. GV has to be positive if we use this contribution 1 plus GV. The allowed range for GV is in this range, about 10% compared to 1. Okay, so this is in the context of this, with the assumption that this scalar coupling and the tensor coupling, because they are related, they arise from the same diagram, they are related at the scale of the leptoquark mass, we can compute the scalar coupling to the tau. By the way, the new contribution assumed to only affect the tau decay, not the electronic decay and the muon decay of B meson. Okay, so this is the plot of imaginary versus real component of the scalar coupling. And you see that real of GS very close to being 0 is what is preferred when you combine RD with RD star. Okay, yeah, that is also shown here. This is the absolute magnitude of, yeah, this is in the plane of imaginary of GS tau versus GS mu. Okay, this is what we have to fit to the model. Okay, this is a simple, I just extracted what is needed for RD and RD star. And as I said, the scalar coupling at the scale of the leptoquark mass is given by this. And as far as RD and RD star, these are the relevant couplings. And we will fit that. I think we will, as I already mentioned, this F21 has to be very extremely tiny from mu to gamma constraint. So we will just fit with the other two. Now, since we have a theory with the 2 leptoquarks, I should also make sure that this other leptoquark does not affect it in an adverse way. The S3 will actually contribute through this row 1/3, but it gives the new contribution will have the wrong sign. So we have to choose that relevant coupling to be smaller or S3 mass to be higher. And in any case, these other couplings are constrained strongly by DD bar mixing and B to K nu nu. So we found that this once we impose these conditions, S3 will not upset the R2 contribution to RD star. For RK star, it is coming from the S3 leptoquark, the 4/3 component. It is the diagram. And this has a feature that the induced coupling is of this type C9 and C10, which is the preferred value for explaining the RK. C9 is the coefficient of the SL bar BL, mu L bar mu L, and C10 is shown here. And there is a preference of C9 equal to minus C10. And this is the C9 equal to minus C10. If we do effective field theory analysis and explain to B to F mu mu transition, that is what one would find. For example, C9 equal to C10 is quite bad. It will give a bad fit to the RK anomaly.
Excuse me?
Yeah.
In this analysis and in the previous analysis, do you include the RG evolution from the leptoquark mass scale to the?
Yes. Yeah. Sorry. Yeah, we did evolve it. So these conditions are imposed at the leptoquark mass scale, and then we use the RG evolution to go from the leptoquark mass scale to the. Yeah, I should have included the expressions, but I don't have it here. But thank you. Yeah, we have included these expressions to go to the B meso mass scale.
And for the next slide.
Yeah.
Next one more. Yeah, here do you also do you also include B sub S to mu mu or not?
Okay. So B sub S, that's a good point. It's yeah, we checked. We did not do a global fit, including the B sub S to mu mu, but we checked that once we get the RD and RK. No, sorry, the RK and RK star fits come out. We check that it doesn't upset. It doesn't make B sub S to mu mu worse than what it is. But by the way, the standard model. This is another clean observable that is claimed to be a clean observable B sub S to mu mu, because the only uncertainty there is the overall decay constant of B as meson. And that has been well determined by lattice calculation. And my understanding is that currently the experimental value is about 2.3 sigma below the standard model expectation.
Right.
And the way of keeping C9 equal to minus C10, it slightly improves this, but it doesn't do a lot more improvement as far as B sub S to mu mu.
Okay, thank you.
The Altman Schofer and company have done this global fit without specifically, by keeping all these operators. They quote overall improvement with C9 equal to minus C10 is something like 4.3 sigma if we don't include BS to mu mu, but it becomes 4.6 sigma improvement if we include the lepton flavor universality violating observable as well as B sub S to mu mu. So yeah, we did not do that in our fit, but it is expected to be kind of consistent with the C9 equal to C minus C10 structure. Is that acceptable, or do you may have more of an expert? You may have more to say.
So this plot just consider RK and RK star only.
Yes, this in this plot. Yeah, this is only this is. I should say that this is somewhat of an older plot. I think before the Muon 2021. So this is just to illustrate that C9 equal to minus C10 is a better fit.
Okay, thank you.
Yeah. So that's yeah, C9 equal to minus C10 is what happens with this S3 leptoquark, and as I already mentioned, this product is Y22, Y32 will give this explanation. And so since again we have two leptoquarks, we have to ask what about the other leptoquark? R2 has there is a component, a 2/3 charge component. If it contributed, that would generate C9 equal to C10 for that contribution. at 3 level. And that's not good as shown here. C9 equal to C10 is not a good fit. These lines intersect at the wrong place. So we have to make sure that we don't, the contribution corresponding to these locations is not exceeding what is needed. So it is it's further. So one might think that having 2 leptoquarks, there is more freedom, but it's not completely true, because if there are 2 leptoquarks, they can affect potentially the good thing 1 leptoquark does. So we have to, this is used as a constraint in our fit. Okay, anomalous magnetic moment. This is the effective, this is the omega 5/3 is the one that is relevant for this one. You can have emit a photon there or from the top quark line. And this is the structure that is the dominant contribution. And what we found is that to get the central value of the muon G-2, this product of this coupling for 1 TeV leptoquark should be of order, it should have a certain sign, and this product should be 10⁻³ roughly. It is not too much of a demand. It's only 10⁻³ because we have big enhancement with that from the top quark inside the loop. So so this for a 1 TeV leptoquark. So all these are now okay. Now that comes the constraint. Because we are doing flavor physics, and flavor is, flavor physics typically explore physics scale or new physics scale of order even 1000 TeV. So having a 1 TeV leptoquark is not easy to accommodate all these. So the various processes that we had to confront are lepton decay, radiative lepton decay, mu-e conversion, V to tau, rare D decay, d bar mixing, bound from kaon mixing, Kaladi constraints. So I will go by these very quickly. These are our well-known constraints. If you have a leptoquark, they can lead to this mu-e gamma. That's the most significant of all these experimental constraints from of this type. Decay width is given, the branching rate for, I don't know why I have 2. Okay. So what is written down here is that this is one of them is a chirality conserving contribution. The other one is a chirality flipping contribution. Actually, one should include the 2 cases together, and we make sure that all the couplings are within experimental limit. For example, branching ratio mu-e gamma, the limit is 4 × 10⁻13. It puts a constraint on this product. FQE, F star Q mu should be 4 × 10⁻4 if the mass of leptoquark is T. Similarly, F times F prime. Well, F prime, I should have defined it here. F prime hat is F prime times the Kabiwa CKM matrix. That has to obey these constraints. There are constraints from S3 leptoquark from this kind of processor, but they are much weaker by a factor of 10 or so, because the couplings needed to explain RK are weaker, and or the mass of S3 could be higher, a little bit higher. Mu-e conversion occurs through, this is a U quark coming in, U quark going out, so it's a nucleus, and mu becomes an E. That puts, there are, this is, well, Fermilab is now going to be running an experiment which probes this at deeper level. Current limit from PSI experiment on this branching ratio is 7 × 10⁻13. That translates into this product, 1 times 1, 2 on the Yukawa coupling is 8 × 10⁻6. So we have to be consistent with that. Z to tau gets modified through a top quark and a leptoquark loop, these diagrams. And we found that this is this puts a constraint for 1 TeV leptoquark. The F prime 3,3 should be less than 0.8. Again, showing that it is you cannot take values much bigger than 1. Some of the earlier literature used for this couplings values like 1.5. That may be questionable now. Rare D meson decay, we have 2 processes to worry about, D0 to mu or D plus to pi plus mu. And these are the decay diagrams. The individual coupling Y22, and this actually constrains not just the product of 2 couplings because of CKM mixing. see, if you have Y22 alone, it induces a Y32 because of stoichiometrics. Therefore, Y22 itself is constrained to be less than this. And for D to pi mu mu, this is a slightly bigger, stronger constraint. So we have to be consistent with that. Other constraints, DD bar mixing through the leptoquark at 3 level. It puts this limit. And it can also arise through S3 leptoquark. K long to mu E, yeah, you see that there's a whole bunch of low energy constraints which we have to be consistent. Luckily, it turns out that it's not just something very difficult to, and none of these is very difficult to satisfy. But we have to be consistent with that, which we did. For example, there are other decays, lepton number violating K long decay, E mu, that puts a limit on F prime 21, F prime 32 at the level of 10 to the minus 3 for TeV leptoquark. Could I ask how much time I may have? Do you want me to hurry up, or do you have? I think it looks like I may have another 10 minutes, but I don't want to go over time if it is too much.
Yeah, I think it's okay to use 15 or 20 minutes. Okay, all right, thank you. Yeah. Now the LHC constraints are, this is the pair production of leptoquark, blue going to, this is independent of the Yukawa couplings. The only, well, the first two are independent of Yukawa couplings, but the last two are also functions of Yukawa couplings. And I already showed that this plot from those pair production. I don't have anything more. This is just to repeat that these models should be subject to these constraints. And I also showed this limit from PP to the T-channel non-resonant production L plus L minus. And we have to be now consistent with these limits. Okay, for any given, say, 1 TeV leptoquark, we don't want any of the couplings to be, well, any of the couplings involving the first generation or the second generation quark. If it is a third generation quark, it is okay to have order 1 coupling. And if there are taus in the final state, which is indicated by the second index, then the constraints are much weaker. Okay, so within the context I mentioned, this is what we needed for, say, RD and RD star for the couplings F23 and F prime 33. It is a product that is going to explain the RD anomaly. And here, this plot is made for the one of the couplings is kept fixed, which is at the upper limit from flavor violation constraints. And mass is as low as allowed by all these constraints I showed you. And there are various exclusion regions, say tau to mu gamma. This is the leptoquark search in the final state, JJ nu nu. This is BB tau tau leptoquark search. The triangle region here is the allowed region, which is consistent with all the experimental constraints, the flavor constraints, and RD and RD star. So there exists, a non-trivial thing is to show that there exists a region which is consistent. And a numerical fit, and I don't have a similar plot for RK because it is just, we can fit to the central value of RK. A numerical fit for these is given here. The 3 matrices, we have 2 examples, texture 1, texture 2. And so if you look at it, you can see that the 3 element of F prime times the 2 element of F, that explains the RD, which is the most significant deviation from the standard model. And things like this minus 0.29 times 0.0059, that product explains the Muon G minus 2. And this Y couplings explain, product of these things explains RK. And the remainder are needed to explain the neutrino masses. So the neutrino masses, we made sure we did a fit to a global fit to all the neutrino oscillation parameters. And with that choice, the 2 fit 1 and fit 2 is giving essentially central values for the neutrino oscillation parameters. So it is consistent. Further collider implications is that these we have this came as a connecting field.
we have a Higgs quadruplet, which has a double charge scalar. Now, this double charge scalar will decay to same sign dilepton or to WW. This is very similar to same sign W. It is very similar to the type 2 seesaw. Now, one difference is that the coupling, when it decays to L+, there is no direct coupling to lepton. It is a neutrino mass generating diagram. It's exactly the analog of that. The partner of that will induce such couplings. And those Yukawa couplings with charged leptons will be precisely proportional to the neutrino mass over this vacuum expectation value of the neutral component of the quadruplet. So one can generate this kind of diagram similar to the type 2 seesaw. Here is a region where it decays to 2W, to the same sign dilepton, and here is a cascade decay as a function of the induced vacuum expectation value of the Higgs quadruplet. So this is one way of testing it. But there is another interesting way of because it is connected to this leptoquark, and leptoquarks can be produced by strong force, strong interaction. And using the cubic coupling, we can produce, sorry, it's a little bit small. We can produce this double charge scalar through one leptoquark goes to another leptoquark, and there's this delta minus minus, and that decays to same sign dilepton. So the reach at the future LHC upgraded luminosity for a double charge scalar is much higher. And here is for 13 TeV, 14 TeV. One can go up to about 7 or 8 TeV in the mass reach for the double charge scalar, which is significantly better compared to the type 2 seesaw. Okay, so that kind of concludes my my unified picture. And in the last maybe 2 or 3 minutes, I want to give a flavor of this thing which we are also excited about. So maybe a connection between neutrino magnetic moment and muon g-2. So this is the yeah, okay. So the idea is that there is an anomaly in the scattering in the xenon 110, which seems to have observed some anomalous excess in the 1 to 7 keV range of the electron energy. This could be from due to some magnetic moment in the neutrino, and the neutrino production being occurring inside the sun. And the value of the magnetic moment that is needed is about 2 × 10⁻11 Bohr magnitude. We actually wrote a paper explaining that with Lindner over here, Jana and Lindner. We looked at it and came up with some natural way of explaining the neutrino magnetic moment. Well, the problem with the large neutrino magnetic moment of this type is that it has the same chiral structure as a neutrino mass. So if you remove the photon line from the diagram that induces a magnetic moment, you will get typically a neutrino mass of order 0.1 MeV. That is too much. There has been, this has been studied long ago, including some papers from the 80s. I wrote one of the papers after Voloshin suggested some an SU2 symmetry, which will prevent the neutrino mass, but allow for neutrino magnetic moment. That SU2 symmetry should include, according to Voloshin, it should include neutrino and nu C should be, the right-hand neutrino should be paired into a single multiplet of some sort. Actually, we found that actually much easier to do a transition magnetic moment between nu E and nu mu. Then you can use a horizontal symmetry that can suppress the neutrino mass relative to the magnetic moment. And this was actually developed further in a recent paper last year. And very recently, about a month ago, we wrote, we didn't realize that initially, but it turns out that the neutrino, sorry, that if you get the neutrino magnetic moment, you predict the muon g-2. The sign is fixed and the magnitude is very constrained. So I want to show that. So this is again, as I mentioned, I will be brief. The standard model with an SU2 horizontal symmetry, the first 2 family leptons belong to an SU2 doublet. Third family lepton, the tau, the left-handed and right-handed fields are SU2 horizontal doublet. The third family is singlet. And then you need, you need to generate neutrino mass and magnetic moment. So this is the standard model Higgs doublet. Then you have this is a generalization of the Z model. Generalization requires 2 copies of these doublet and 2 copies of this eta plus, because I need to have an SU2H. This is the model, and it provides Yeah, if you look at the neutrino magnetic moment, this is the diagram that generate neutrino magnetic moment. If you remove the photon line, these two diagrams will precisely cancel. So there is no neutrino mass contribution. But there is a partner to this diagram, which are these diagrams shown here, the neutral guy. And if the neutral guy is emitted, it has the right sign. And it's only the neutral guy that can have significant coupling to the muon. The other couplings are constrained from the charge guy. There is also a charge guy here, but that is constrained from neutrino mass or lepton flavor universality. So we looked at this, and this is our final result. Here is a neutrino magnetic moment in units of 10 to the minus 11 Bohr magneton. Xenon 110 excess can be explained in this region. And here is the muon magnetic moment, anomalous magnetic moment of the muon. And the combined experimental average is here. And these are the shaded region are the ones that this model predicts. What is needed, I won't have too much detail, but what happens is that in order to generate this, these scalars have to be relatively light. This phi 1 naught and this partner phi plus and phi naught, these are additional Higgs doublet. They must have mass below about 200 GeV. And if you look at it, that is not inconsistent with current data because they couple the first two families with the third family. So the best way to study this model at high luminosity LHC would be to look for resonances that decay to E tau or mu tau. It can be done, and the reach of this particle mass of that LHC is of order, I don't know if we show that here. No, that was, I don't have the figure here, but it can go up to about 400 G. So sorry to have taken a little bit more time than I thought. This is my conclusion. Simple one-loop neutrino mass model utilizing TV scale leptoquark can explain the B anomalies. The same model can also explain the muon G-2. The Higgs quadruplet is interesting. It provides interesting collider signal, especially with the same sign dilepton with a higher reach. The model is constructed to be consistent with neutrino oscillation data, and I also briefly mentioned about the connection between G-2 of the muon and anomalous magnetic moment of the neutrino. Thank you very much.
Thank you for the detailed talk. Are there questions or comments?
I have a question.
Yeah,
hi, thank you for your interesting talk. So in a in a leptoquark sector, there are many Yukawa couplings in there, and in principle they can be complex.
yes.
Then I'm wondering if there is a contribution to electron EDM.
Yeah, that's a very good question. So in fact, in the fit itself, we have a complex value parameter. So actually, we looked at it. In fact, when in our first draft, we had not included that. Actually, referee asked us precisely the same question. So is there any a signal of CP violation that is available in the model? And the actual answer is yes. However, with the flavor constraints highly already constrain the first row and column. So the electron-electric dipole moment is not, we don't predict observable electric dipole moment of the electron. What we do predict is some significant contribution to the electric dipole moment of the muon, because this is occurring in the muonic, it affects the muonic sector first. We evaluated that, and I don't have it in my slides. I believe it is at the level of 10 to the minus 22 e centimeter for the muon electric dipole moment. So that is potentially in the observable range. Current limit is few times 10 to the minus 19 Bohr magnet, e centimeter for the muon electric dipole moment. Yeah, so it is an important thing because we do have this complex couplings. Thank you.
I see. And also, this is just out of my curiosity, but if you want those leptoquarks derived from some gut models, one should make sure that all of the couplings should remain perturbative up to the gut scale.
Yeah, okay. Yeah, that, no, of course, yeah, I'm also very interested in that question on, I should say that this is my personal opinion that these leptoquarks at the moment, they are constructed in most models are not quite compatible with GUTs. And the main reason is that once you have leptoquark, they can also, many of them tend to also behave as diquarks. And the same particle being a leptoquark and diquark, as you know, is that will lead to proton decay. So the bottom-up approach, I think what most models do is assume baryon number as a good quantum number. It just, and that is not compatible then with the standard grand unified theory. But if you don't if you're not thinking of actually unifying the leptoquark into a multiplet, you can still ask this question of, is this perturbative all the way to a very high scale? And I think these couplings that are shown here is perturbative. Because from perturbation theory point of view, all that matters is that coupling which are of order 1, right? So I have 2 couplings which are explaining the RD anomaly. Here is order 1, here is 0.88. And having 2 of these couplings at 2 different locations, I believe is okay. I mean, this is like similar to the top Yukawa coupling, which we know is its value at the gut scale is somewhat smaller than this value at the weak scale. Although I haven't actually checked it, but I'm pretty confident that this can be extrapolated to very high scale.
Yeah, in that case, well, electric vacuum stability will be some concern. Right.
Okay, that is a much more complicated problem.
Yeah.
We do have so this is the multi-scalar model, right? So
right.
we looked at in our paper, we have details about all the Higgs potential. And as soon as one has another scalar that couples the standard model Higgs, it is possible by choosing the quadratic couplings appropriately, it is possible to extrapolate it beyond the 10 to the 11 GeV where the standard quadratic coupling would turn negative. So I think, yeah, there is some room for this, but we have not studied it. It's a rather rich Higgs sector. Yeah, it could be interesting to study this. Yeah, I would like to find out, is this kind of flavor structure, is it believable? I mean, this purely from bottom up. It is adding to, there is a big flavor problem, right? Why the electron is so much lighter compared to all the other fermions. Now, if this is true, I mean, experiment may be compatible with this, but we are adding too much, quite a bit to the understanding of the flavor factor. So yeah, I think, I mean, I would take it more seriously than a toy model, but if you ask me, is this the ultimate model of the universe? I'm not sure. If you go by experimental facts.
Yeah, thank you very much.
You said that you cannot fit the low Q² bin of, I think, RK star it was. Why is that? Just because the propagator suppresses the value too much?
Then if you do that for the low Q² bin, if you explain, then there will be by a resonant production, then above the resonance, you won't have this effect. I mean, the rate would be suppressed. So unless you say that there is some effective dimension 6 operator that is explaining the higher Q² bin and a resonant light particle, which is with a mass of, actually there is one paper by Pospelov, Altman Schofer and company, which has actually done exactly this. They try to explain along with the high Q² bin, the low Q² bin, and they found one particular location in the mass close to the muon mass. If the mass is around there, they can also fit that. But that, it requires 2 mechanisms. The same mechanism cannot be applied to higher values.
So in your model, you say the high Q² bin is close to the resonance, and that's
no, we don't have any resonance. So everything is at the 1 TeV. The resonance means really at 100 MeV of order, some particle with a mass of order 100 MeV. We don't have anything in this model. So we don't, So the short answer is that no, we don't explain the low Q² bin. Now, I've not really studied it in detail, but I've seen statements to the effect that the low Q squared versus the high Q squared bin may be made compatible with each other by tuning some of the form factors at some 2 sigma level. There is a parameter called A2 form factor. By taking their A2 values to within 2 sigma, the discrepancy between the high Q squared and the low Q squared may be minimized. That is a statement, but I have not really studied it. So it may be not. It may be that the high Q squared values is considered to be a clean observable. I'm not sure if it is exactly true for the low Q squared.
One more, if I may. How does the difference between, say, D and D star enter in the calculations? I mean, the quark content is the same, right? So the Feynman diagrams will be
so
the
the
same?
difference appears with the matrix element, because one is the pseudo scalar, the other one is the vector boson. So in one case, if it is a gamma mu gamma phi that is contributed, in the other case it will be gamma mu term. So because of that, the V minus A or V plus A will make, it actually can flip the sign. And in fact, so there are models there which have attempted to explain RD, including one of my papers with Mohapatra and Datta. We tried to explain the RD anomaly using V plus right-handed currents. But there it turned out that there was no interference term. It was coming from the absolute value squared, non-interfering terms. Then this was not an issue. Because pure V plus A matrix element is the same as pure V minus A matrix element. But if you are looking at the interference, this is important.
Okay, thanks.
Other further questions or comments?
Yes, sure.
Just a quick question. In around page 30 of your slide, you mentioned Z2 tau tau. Does it mean it can have an impact on the B2K tau plus tau minus rare decays?
Oh, B2K tau plus tau minus.
Yeah.
Yes, or a related quantity would be B sub S to tau tau. Yes, these are modified. These are modified in this context because, yes. However, at the moment, the current limit or the constraints on these are way off. This the branching ratio, for example, I don't recall that B to K tau tau, but for B sub S to tau tau, experimental limit is at the level of perhaps 10 to the minus 2 on the branching ratio. And this will predict something at the level of 10 to the minus 5 or 10 to the minus 6. Which is much bigger than the standard model, but still way smaller compared to the experimental limit.
Okay,
yeah.
Then what about building a giga Z machine, giga Z E plus E minus machine in the future as a future collider?
For searching for, of course, lepton colliders are good for everything, right? Because of precision studies. We haven't actually looked at the reach of E plus E minus or perhaps mu plus mu minus colliders to these things. Others have studied it. It's my understanding that since the I think in maybe I should break it up. I was giving a unified picture, but perhaps you're asking more generally. I think RD is the one that requires really low scale physics because if we want to be within perturbation theory, I find it that in order to explain RD, must have some new physics below 2 TeV. But RD, RD is not so much connected with the muon collider because it treats muons and electrons in the same footing. RK could be happening at, in terms of dimension, in terms of the effective field theory operator, one could have the new physics scale to be at of order 20 TeV or even 30 TeV. But if you really realize it within a model, it's not really going to be 20 TeV because there will be a suppression of order VCB or something like that, and it will lower down. In the model that I presented today, the RK would require it to be less than about 3 TeV, 4 TeV. So that's a good place to think of a muon collider. For example, that can be directly probed. Now, as far as a muon G-2, actually, there's something interesting. I think you folks probably also had some talks. I'm sure that every place had a talk on muon G-2 recently. This question is something that I find it very interesting. What is the maximum scale that new physics that explains muon G-2 can be? Just as I mentioned very briefly at the end of my talk, if you generate muon G-2 through the chiral flipping of proportional, say, top mass or some other fermion mass, you might think that you can raise the new physics scale to higher value. But for the same reason, if you remove the photon, you will just generate a muon mass. And if you demand that the induced muon mass is not more than the physical muon mass, I think you will get something like 5 TeV for the maximum scale of new physics in a natural way. So again, that could be something that is very relevant for muon colliders.
Thank you.
Kaladi, I have just a naive question. So suppose RD star disappear in the future.
Disappear in the future, okay.
Yeah, and then within your approach, what can you still
okay.
Just
the
the
same
RD disappears.
Yeah, so then one of the motivations of this model may be a little bit less.
Mm-hmm.
And the reason is that, so in these matrices that hopefully you can still see, it is F times F prime. These are couplings which were related to the RD star. And we were able to get the muon G-2 by the same matrix. So now that field is no longer as well motivated. But if I can still think of using the same field, but if RD star goes to smaller value or maybe disappears, what I would have to do is make these blue numbers, order 1 numbers, make it a little bit smaller. Then the model can stay. Yeah, I adjust those numbers to smaller values to fit whatever observation for RD.
So you are still going to keep two leptoquarks in the case.
So this is So
neutrino mass ready.
This is simply coming from the neutrino master.
Oh, okay, I see.
Yeah, neutrino. So I don't think I will get a much simpler model than this. 2 leptoquarks are needed. If I use 1 leptoquark, that's not enough to generate neutrino masses.
Okay.
So yeah, I think the simplest way scenario would be I will choose adapt the same model, but simply choose smaller couplings here in the 1.06, 0.0. Those 2.
Yeah, I was just curious because when you show the RD star anomaly current status of the RD star, the most recent data from Bell is getting close to the standard model predictions.
Okay, I see. Yeah, no, I think we are eagerly waiting for Bell to tell us more. And yeah, there has not been any update from the LHC side on this, at least in the last year. So we are still going with the older numbers. Yeah, that is interesting. Have they published any, either any preprint on that or RD star?
No, I don't have any idea. Maybe Yongjun knows.
I think the latest one is spring last year from the.
I see. I see. I'm sorry, I couldn't hear well.
I think it was some noise, but anyway, what I said was, yeah, the latest one was the spring last year.
I see. Thank you.
Further questions or comments? If not, let's thank Professor Babu again. Thank you.
Thank you very much for listening.
you.
Thank you. Bye bye.
Okay, bye-bye now. Stay safe.